Mike?
Okay, well, thanks everybody for joining us tonight. Like I said, there's a couple of guys still missing in action, but they'll probably join a little bit later. I don't know, Dave, do you want to introduce our guest tonight? No, your mic's off again.
Yeah, darn that mute. Yeah. So I'm sure Sean is going to talk a little bit about how he met us, but we kind of met at FDIM, and he's a staple. He's a, he's a core part of. Can everyone mute their audio? Yeah, thanks. So yeah, so I think we're getting some feedback.
Frank, do you want to mute? Frank, do you want to mute your mic?
Okay.
Okay. Yeah. Okay. Sounds better. So yeah. So we met Sean at FDIM. We've been going there now a number of years, and we see Sean there almost every year. And we've been socializing with him, getting to know him, and some of the work he does. And he's a very interesting fellow. Does some very interesting things. And we invited him to chat tonight about some of his experiences and what he does, and he graciously agreed. So without further ado, I'll turn it over to Sean, and Sean, take it away.
Okay, well, let me see. I will share screen. How do I do the whole thing here? Entire screen. Okay. I was advised to always share the whole screen just because it makes it work better. So I'm going to try to do it that way. And I will start the presentation. So I guess I titled the presentation about light study and application in science and the arts because that's kind of a good description of what interests me and has appealed to me all my days, really. I currently live in Hawaii, in Kona, on the Big Island, and I work largely from home. I've been doing that since 2016, so I didn't start doing it when the pandemic started. I started it before that. It's a great way to be. So let me see what I wrote for the first slide. So my background is I have over 40 years of experience in optical, mechanical, electronics, and software engineering. I have 17 patents issued or applied for in optics, mechanics, and software. My first job out of university was as a lighting designer and assistant designer for the Broadway Theater. I always loved the theater when I was in high school, and then I continued to do it as my sort of undeclared third major in university. And when I completed university, I decided that what I really wanted to do was try to pursue a career in theatrical lighting design. So I packed up my 6.5 cylinder Ford Fairlane and removed the $1,500 that was in my bank account and drove to New York and went from there. I had joined the Stagehands Union while I was at university because we had a theater that did Broadway road shows. So I was able to start by working as a stagehand to keep from starving while I figured out how to get into being recognized as a professional lighting designer in New York. As a parenthetical note, at that time, being a stagehand was a pretty good job. The only it was considered a blue collar job, although you really had to have a degree from at least a 4-year college to get in at that point. The only people that got paid more were the garbage collectors, the Teamsters and the garbage collectors. So we did pretty good. Anyway, I ended up taking my engineering knowledge and using it in the theater. I ended up with what I called a day job as the chief engineer at one of the companies that provided lighting equipment on a rental basis to the Broadway Theater and to their national tours. And because I was fairly current in engineering and particularly in computers, that came in handy, and I was involved in the development of some key technologies in entertainment. Subsequent to that, I got tired of the kind of combative environment of the theater, so I decided to go ahead and move to Vancouver, British Columbia, where I started working for a company that designed and built theater and television lighting control systems. And then from there, I segued to starting my own company to pioneer the development of digital technology for motion picture films. I sold that to the IMAX Corporation in 1998 and had to work for them for 4 years to be sure I would get all my stock options. And then I moved to Hawaii to take a job at the Keck Observatory, where I became the manager of the instrumentation program. I'll come back to these other observatories later, but these are the major observatory projects I've worked on since moving to Hawaii. And then I've been an extra class amateur radio operator for the past 24 years, and I'll explain that as I go along too. So I got started by doing what probably a lot of you did, or at least some of you did. As a kid, I dismantled the discarded televisions that showed up in the alley behind my house. For parts, I built radios, hi-fi amplifiers, and simple test equipment. I also was convinced, shall we say, by my parents to take up the violin at age 6, and I played it through high school. I'm actually part of a musical family of 8. I'm the oldest. My father and my stepmother were both professors of music history. Current famous people in our family, I guess, would be my brother Christopher, who's the principal cellist with the Dallas Symphony, and my sister Madeline, who's the concertmaster of the Utah Symphony. Even though there was plenty of music around, I was really more interested in science and engineering. Of course, I read a lot of science fiction books and so on too. And I was really fascinated by inventions and inventors. I guess I have to say that my earliest inventor hero was Thomas Edison. And then there are, many others since that I've read about and studied their body of work. I got involved in theater in high school. And then at university, I studied computer science, physics, then electrical engineering, and I did lots of theater, sometimes to the detriment of my grade point, but it was fun. And then later on in life, I got a master's in business administration with an emphasis on technology management, because as I went along, I found myself doing more and more of that, program management, getting funding for things, and so on. So in my early career in university, I started in the mainframe and mini computer era, but I was exposed during that time also to the beginning of the microcomputers. I started with computer science. I finished that degree, and I had gotten a full tuition scholarship to university, I should just mention. And so I had the funding for 4 years, but I finished the computer science degree, and I had, I think, 3 semesters of tuition left. So then I did electrical engineering because I wanted to know how to build computers. I've also always been interested in computer music, since I obviously have a music background. And then all of this led me to using computers to control lighting, which is one of the main things that I did when I was in New York. Was I helped, along with the chief engineers at 2 other companies, to transition Broadway to a fully computerized lighting control system, which matched more what was being done elsewhere. But the Broadway stage had been very backward because of the strong influence the unions had over, the stagehands union had over how things were done. But we broke that down. And I've always been interested in technology-based art forms and the power of art to humanize the technology, which I think is a strong virtue of the connection between art and technology. So if I wanted to have a thread through my career path, I guess it's light. It's first as a lighting designer and someone who studied and understood how light worked in a practical sense. It's a pervasive and visible demonstration of the effects and uses of electromagnetic radiation. What we can see is, of course, just a tiny fraction of that spectrum. Light's a tool for studying the universe and our world, and I'll talk more about the universe part in a moment. And I think it's a powerful tool for human expression. It certainly is used in a variety of ways to make our architecture more appealing in our cities and so on. And it's also, of course, a very much a part of our live entertainment experience. So radio, where does that come in? Well, I had an early interest at age 5 or 6 in shortwave listening. A few years later, I built a night star roamer. Some of you may know that thing. And I modified it to use IF regeneration for a BFO per an ARRL handbook idea. I stayed interested in electronics, but not specifically radio through university. And I did all along here continue to do shortwave listening and with various, transistorized radios. And one of the things that I was always interested in and did less of than I would have liked by university, of course, there were no vacuum tubes except really high power tubes and, magnetrons and things like that. So it kind of harkened back to my early interest in shortwave listening and tearing apart TVs to build things. I decided I'd like to have an antique radio. And so I went hunting for one in the antique markets in Vancouver, and I found a nice RCA with shortwave and a tuning eye, which I developed an affection for. And that led me down the slippery slope of collecting something. And I joined the Antique Wireless Association. You know them from Rochester, New York. And at an auction at their 2001 conference, I bought a cute little LMAC AF67, which you probably know is an AM transmitter with its own BFO built in and so on. So because I was collecting and restoring antique radios, and I firmly believed in two things. One, I wanted a radio that nobody else had tried to restore, so I could hopefully do a good job. And the second thing was that if I acquired a radio or anything else with tubes in it, I wanted it to work. So, of course, this was a transmitter, and I thoroughly knew the regulations regarding that. So I needed to fix it up and do something with it, which led to getting a ham license. So that's how I got my license in, let me think here, in 2000, 2001. Yeah, 2000. Yeah, it's 2000. It's 24 years. Sorry. Anyway, I got a pretty good station together. It was then and still is all vacuum tube. And when I was in Vancouver, I did quite a bit of AM and CW and sideband. And after moving to Hawaii, I was DX for a little while, and then the solar cycle was on the downswing. So QRP looked like a fun challenge to do when I was on the mainland, since obviously I was just going to do local QRP in Hawaii. But I did it for the usual reasons. It's easy to build things when you're using low power. It wasn't mostly tubes, but by then I had a grudging admiration for transistors. So I found QRP ARCI, and in 2015, I went to their 4 Days of May conference and at the Dayton Hamvention. And I met these fine fellows from your club, and they sort of adopted me, and we've been at least friends and that see each other at the FDIM and the Hamvention each year. Of course, Eric and Peter and Dave and Cherry and Kevin and myself, and the other Dave is taking this picture. So we enjoy meeting up there, I think, and have a lot of fun. So I'm going to talk now about astronomy because that's mainly what I'm working in. And I thought it'd be fun to talk a little bit about what is interesting to me about astronomy and how the technologies that we use are related to that. And basically, astronomy has a lot of questions it tries to answer, and it tries to use theory to develop explanations for why things are the way they are. And then you do observations to test whether your theories are correct. And sometimes just random observations, which is where pretty much all astronomy started, led to needing to develop theories and understanding to explain what you were seeing. And I won't read all of these, but these are many of the very common questions that we try to answer. So there's a number of different disciplines in observational astronomy, which is what I'm going to talk about now, because I'm definitely not a theoretician in this field. And of course, one that's near and dear to our hearts is solar astronomy. And we like to know when and where the sunspots are coming along. We like to know what the solar wind is doing, and are we going to have a disruption in communications? like the CME that we had on the 16th of September. I guess that's the most recent one. And so one of the projects that I worked on that I'll come back to later is called the Daniel K. Inouye Solar Telescope. It's the largest solar telescope in the world at 4-meter primary aperture. And you may know something about the structure of the sun, but it's kind of nice to know when I show you these images where they're coming from. So this is an image of the photosphere of the sun taken using the Daniel K. Inouye Solar Telescope and its adaptive optics system, which I'll explain later as well. And that's a sunspot. So I think this is a really cool picture because it looks like something that Chihuly or some other glassblower might have created. But this shows you the temperature change that occurs as the material wells up from inside the sun and then collapses into the center. And there's always a magnetic anomaly associated with this, which is where you start to get into things like coronal mass ejections. So this is on the photosphere. Then the chromosphere, which is the lower layer of the sun's atmosphere, is also pretty fascinating. In this image, you can see these little bits of look like little threads, and work done at the Daniel K. Inouye Solar Telescope Observatory has shown that these map magnetic fields in the interior of the sun, and those fields are expressed on in the lower atmosphere of the sun.
John.
Planet. Yes,
John,
sir.
I think
Yes.
we've picked up your full screen of something else. We're not quite seeing the picture that we were a minute ago. Okay, that's in the background. At the foreground it looks like it's all your. It's like something's happened to the sharing of the screen. There we go. Now we're there.
Well, I didn't touch anything. I don't know.
No.
I can't see what I'm showing, of course, because I'm
Well, it's
looking
okay
at my
now. Yeah, it's okay now.
All right. Okay, so planetary astronomy, that's the study of the nearby planets. Planetary astronomy is interesting to us because we can look at the planets that we are that are here with us around our sun, and we can get some insights into how that that happened. How did we end up with this solar system with these particular planets? But there's more we need to learn, and we do that from other forms of astronomy. But this is an image of Uranus. This shows it has a ring. These are actually clouds on the surface, and that's one of its companions. And then this is images of Neptune. And what's interesting about this, among other things, both of these two images, by the way, were done with adaptive optics at the Keck Observatory. These images show the change in the cloud patterns on Neptune. And it turns out that there's about a 2-year lag between the peak of UV emissions from the sun during the solar cycle and the appearance of clouds on Neptune. And then, of course, as the solar cycle declines, the clouds begin to fade. So this is a pretty interesting set of observations. Then stellar astronomy. Well, that's the study of stars other than our own, and how stars form. And they basically form from clouds of gas and dust being disturbed into starting to condense, and then they collapse into a tighter cloud because of the gravitational attraction of the particles in the cloud. Eventually, this collapses to the point where it starts to rotate and forms a disk. And after a period of time, these are the number of years it takes for this to happen, then you end up with a protostar, and then subsequently a cleaning out process of a disk formation followed by accumulation into planetesimals, and then the formation of planets results in a planetary system. And you may have heard, of course, of people saying, oh, Plan 9 from outer space, Planet 9 from outer space, or some other rogue object is going to come through the solar system and destroy us. That doesn't happen because all of the available dynamic space in the configuration of our planetary system is occupied by a planet in an orbit. And although we have the asteroids to contend with, which are the last bits of debris left over from the formation of the solar system, at least in the inner orbits, then there's a whole nother cloud around the outside, the Kuiper belt and the Oort cloud. But in this case, like our solar system, it's dynamically full. There's not room for any intruders. This is an image of a star called Fomalhaut. This is this is a Hubble image. The star is there in the center, and then this is a very large accretion disk. It's thought that this is actually a protoplanetary disk, and although it's been reported that there are some planets orbiting this, it turns out they're both balls of dust and gas still. And then this is an image of a direct image of an exoplanet taken at the Keck Observatory. It's a giant Jupiter mass planet, much bigger than Jupiter, but it's a giant planet like Jupiter, and it's orbiting the sun here. The way these images are done, of course, is that a thing called a coronagraph is used to obscure the star itself, and of course, adaptive optics is used to refine the image to the point where you can see that. Galactic astronomy is really a fun area because you get to study what people like to call the galactic zoo, all the different kinds of galaxies, the different morphologies, some of which are associated with much older galaxies, but most of these are found even today. When you study galactic astronomy, the other thing that you're interested in is how do galaxies form? And one of the leading theories now, based on our own Milky Way galaxy, and in particular another galaxy called M87, where we've been able to make an observation in both cases of a black hole. There's a black hole at the center of our galaxy, and M87 has a black hole at its apparent center as well. So these black holes, which probably originated from early in the formation of the galaxy, are important to understanding how galaxies form and how they evolve. And of course, another topic that's kind of interesting is the galaxy Andromeda, which is 3 billion light years, the galaxy Andromeda, won't worry about the distance, will collide with the Milky Way in about 3 billion years. So yeah, galactic collisions are of mild interest, I guess. Is my video still okay? Can you see the thing?
I'm back to that. For me, I'm back to that screen again where I'm seeing all kinds of windows.
I have no idea what's happening.
Now it just disappeared. Am I the only one that's seen that, or has everybody else seen that?
No, I see it too.
Yeah, no,
Okay.
that's right, Peter.
Did you get to see this?
Yep. Yep.
Okay. All right.
It looks like the task. It looks like the task window when you go to a different desktop in Windows. That's what it looks like, Sean.
Oh, well, I'm not doing anything like that.
Yeah,
I mean, I can only, I will tell you honestly, I can only see the screen I'm sending out, right? That's the way it is. So I don't know about
Stupid
that.
Windows tricks.
Yeah. Okay. Well, if it happens again, let me know. I'll try to just make sure I move the mouse wheel to go. Maybe I touched a button on the mouse or something. I don't know. All right. So extragalactic astronomy. This is a particularly interesting field because this is where we get to try to do things like figure out how old the universe is, how big it is, and so on. And to do that, we look at the most distant objects we can find. And these are the two record holders at present, both from the James Webb Space Telescope. This galaxy is at a redshift of 13.2, sorry, and it's the light from it took 13.4 billion years to get here. This one we don't quite know yet. It's too new of a discovery and the data analysis is still going, but that's a JWST image. And what's cool about this, I'm sure you've seen this from the Hubble Space Telescope, all of those things you see there, except for foreground objects like that star and that one are galaxies. And it's just so amazing and bizarre that there are that many galaxies, I must say. In any event, one of the things about these galaxies is, of course, they are moving away from us. Everything that is in the universe has an initial inertial push from expansion of the Big Bang, which I'll come back to. And so they're all moving away. And as it turns out, they are moving faster the further away they are. And the light from those galaxies is redshifted. So it's basically what you know from the Doppler shift. An object moving away from you is effectively stretching the wavelengths of the light, and of course sound that it might be producing if it's on the street by you or something, or at the racetrack. So we have to take the spectra of these objects, and then we have to move their spectral energy distribution around until it matches a template that gives us some idea of how far away they are based on their redshift. So the last one is physical cosmology. Cosmology is a term generally applied to try to understand the universe. Theoretical cosmology gets lots of airplay because it's it's interesting, but it's pretty difficult to understand. Physical cosmology is pretty straightforward, although it's on the most massive scale, that of the universe. One of the things that anyone who's worked in microwaves much knows is that there's a fair amount of background noise in microwave, and that comes from what we call the cosmic microwave background. It is a remnant of the Big Bang. It shall we say froze in its present state about 380,000 years after the Big Bang, or the start of all time as we know it. It's very cold. Its temperature is 2.7 degrees Kelvin, so it's just above absolute zero. It's completely invisible to the naked eye, but one of its interesting properties is it has this anisotropic distribution. There are these brighter areas with somewhat greater emission, and there are these dark areas with less emission. What we think this is we think this is the signature of the imbalance that caused the proto-universe to do its thing, to explode. But except for theory, we still haven't confirmed that. But what's interesting is that when you look at the distribution of matter in the universe, you find that it has an anisotropic pattern as well, suggestive of the idea that this relates to the origins. So the idea of the Big Bang, of course, is that there was this explosion caused by we don't know what. And from there, a really brief period of expansion occurred, which gave the impetus to all of the matter in terms of its subsequent expansion. We went through a phase of having actual real matter in the form of hydrogen, a period of the dark ages, they call it. There weren't really any photons because the energy was distributed so uniformly and everything was very cold. But then the first stars and galaxies began to form, and as the expansion continued, they moved apart, and here we are right now. So the size of the universe is a fun thing to talk about. We talk about light travel time usually when we say it's 13.8 billion years. And so that's its age, but its physical size is 93 billion years because expansion has pulled things apart over that 13.8 billion year time. So I'll save anything else about that in case anyone has any questions. So going on. So observational astronomy, I've shown images that you'll notice several of them came from a space-based telescope, in this case, the James Webb. So one of the questions that you can ask, and I get asked a lot, is why do we need ground-based observatories if space-based observatories are better? Well, I'm sure you know the answer to that. Space-based observatories cost incredibly huge amounts of money, and they can't be serviced. We gave up the ability to service Hubble when we retired the space shuttle, and James Webb Space Telescope was deliberately placed at a distance from the Earth where it is better. It's in a better position to be shielded from the sun, and it's in a position where it doesn't need to use as much energy to stabilize its orbit. but its helium supply, which cools its instrumentation, is only going to last 10 years, more or less. We may get lucky and it'll last a little longer. So, and we can't service it. So that's that. So what are the things that you want to worry about if you want to build an observatory and do a good job in the present state of the art, if you like? The things you worry about are, you want sensitivity, you want angular resolution, that is, you want the ability to have detail resolved in the objects that you're looking at. You want high quality imagery because that makes your data analysis process easier. And you want to justify the existence of especially an expensive observatory, then you need to be scientifically productive. And that scientific productivity comes from a combination of having users that are competent, capable, and innovative in the science, from having efficiency to do observing well and not waste time, to have good observing capabilities, and of course to be reliable or to have good uptime. So my little equation for an observatory is, it's a telescope plus instrumentation plus analysis tools, i.e. software, plus a good site and the people. So making progress in this field requires you to do some particular efforts in the areas I listed there. Sensitivity, this explains why we keep trying to build bigger telescopes, because a larger aperture collects more light. The light collection power scales as the square of the diameter. To improve sensitivity, other than by building a bigger telescope, we can try to get higher throughput, allow less light to be wasted on its way through the telescope. So that means for reflective optics, we need better coatings. And for transmissive optics, we also need better coatings, in this case, anti-reflection coatings. And then to get angular resolution, a bigger aperture will do that for us, but only if we can use it. And because of the atmosphere, a ground-based telescope needs adaptive optics. And we need to improve those adaptive optics. Then beyond the adaptive optics portion, which takes care of what the atmosphere does to interfere with our observations, at least to some extent, we want better optics. We want to reduce aberrations. We need to get better alignment. Our detectors need more pixels so they can sample the image better. Then image quality, well, angular resolution is a key to that. The performance of the detectors you use to convert the energy, whether it's in the visible or in other parts of the electromagnetic spectrum. You care about noise, operability, that is how many good pixels you have, how uniform it is. And then you need to worry about being able to read it out quickly, but within a sample depth that's commensurate with the dynamic range of your signal. Scientific productivity, we need to keep training new astronomers and broaden the base of scientific interest. Observing efficiency, I won't say combat anti-science, but that's what I really mean. Observing efficiency, reduce setup time for observations, use queue scheduling. In other words, we don't just say, okay, Mr. Astronomer or Ms. Astronomer, this is your telescope for tonight, carry on, because the weather may preclude doing the observing program that they have decided they wanted to do. Queue scheduling allows the operators of the telescope on a long-term basis, that is over the course of a year, to schedule observations so that they get the best weather. If an observation is weathered out, then it can be done later. Also based on instrument availability, because maintenance is often required, and that otherwise can also prevent you from doing a program you wanted to do on a particular night. Then another aspect of productivity is the capability of the observatory, and that primarily relies on the choices of instrumentation, how much of the sky you can cover with those instruments, and that's particularly important for adaptive optics, which I'll mention in a moment, and of course a field of view that's commensurate with the kind of observations you want to do. And then the last one, of course, is uptime, and the fundamental for there is test, 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 especially software. Improve reliability and reduce the mean time to repair. MTBF you care about it too, but really the thing you want to be able to do is turnaround repairs. You want as many line replaceable units as you can, and you want an adequate collection of spare parts and technicians who can use them to repair things quickly. My video still okay?
Yes, it is, Sean.
Good, thank you. Okay, so the technology for observational astronomy, making progress depends on better performance in the key parameters I just described. Telescopes and instrumentation are multidisciplinary, and that's one of the things that makes it really fun. It's optics, it's mechanics, it's electronics, and it's software. So from an engineer's point of view, these are all things that are fun to work on, and making them work together is also very cool. So what are the key technology challenges for ground-based astronomy? And this is all part of understanding why we can justify building ground-based observatories still. The fundamental reason is because we can develop these observatories and we can upgrade them and we can maintain them in a way that's just not possible with space-based observatories. Now, one day we may have observatories on the moon, and that may change this, but for now, ground-based astronomy really is still one of the strongest ways to get what we want to know about the universe. But we have to contend with the fact that there's an atmosphere between us and the light that's coming to us from the universe. We have to contend with the physical size of the telescopes and instruments. So addressing sensitivity by making them larger ultimately becomes a challenge. We have to take into account when you build something big, among other things, you've got to worry about gravity. Don't have to worry about that in space. You have to worry about noise. And I mean, you know, all of us as ham radio operators know how bad our noise environment has become. And that very same noise environment in the form of electrical noise can in fact interfere with equipment on telescopes. Photons, that's a generation of photons, whether they be visible or not, is a statistical process. And that means that there's inherent noise in the signal. Of course, you can have vibration introduced by equipment or by the wind as it hits the telescope structure. And then there's thermal noise, everything from you know, the actual motion of the atoms in the materials that are used to make up detectors and so on, to diurnal effects when it gets warmer in the daytime and colder at night. And then, of course, the last one is complexity. We have to create these bigger, better systems. That usually means, like everything else in the world, that they're going to get more complicated. And that goes right through, of course, to the software. So a quick digression, I probably won't read this whole thing. I'll just mention that angular resolution, in case you don't know what it is the smallest angle between two objects at which they can be distinguished as separate. And that's crucial, for instance, in trying to observe an exoplanet using a telescope. You have to be able to tell the difference between the planet and the star, if you like. For kind of reference, our eyes have an angular resolution of about 1 arc minute. The angular diameter of the moon is about 30 arc minutes, or half a degree. And of course, if you stick your hand out at arm's length and put the tip of your thumb out, you can just cover the moon. You could do that with the sun too, but you wouldn't want to try that without protective eyewear. The refractive index is important because I just messed up there. Sorry. It describes a ratio. It's a ratio describing the effect of a medium on the path of light traveling to it. And the reference for the ratio is a vacuum. What essentially happens is a denser medium causes propagation of the light to be slower than it would be in a vacuum. And that results, under proper conditions, a bending of the light rays as it transitions from one medium to another. Anyway, refractive index varies with density, and n, that is refractive index, is smaller at lower densities. Refractive index varies with wavelength and is smaller for shorter wavelengths. So angular resolution is higher at shorter wavelengths, and an optical system's angular resolution is proportional to the wavelength divided by the diameter of the system's aperture. The little equation I showed earlier. Due to the atmosphere, angular resolution is limited to about 1 arc second. Whereas at a 1 micron, which is in the near infrared wavelength, a 1 meter telescope has a potential resolution of 1/4 of an arc second. And a 10 meter telescope, like the Keck telescope, has a resolution of 25 milliarc seconds. Neither of those resolving powers come true in the face of the atmosphere. So, technology challenges and solutions. The atmosphere is a challenge. It absorbs some of the light. Transmission varies with wavelength, with water vapor content, and with the seasons.
Our famous screen is back, Sean.
Oh, all right.
No, no.
Transmission varies with time of day and seasons, i.e. hydroxyl radicals or OH molecules. The atmosphere has its own emission lines, and those add to the noise in your observation at certain wavelengths. The refractive index of the atmosphere changes with density, and density varies with altitude and temperature. The refractive index of the atmosphere changes as its density changes due to winds and temperature gradients. And this all causes changes in the path the light follows, which is what, of course, creates the twinkling that the stars exhibit sometimes. They particularly exhibit it when there's a disturbance in the atmosphere, either the arrival or the departure of a cold front, higher levels of moisture, and so on. And so just in terms of turbulence, the kind of turbulence that we're dealing with in ground-based telescope systems has to do with these short time scale disturbances due to convection, air rising and falling due to temperature differences, and of course turbulence. The size of these features is also important because that shows their relationship in terms of how quickly they move across the aperture of your telescope. So turbulence is seasonal, and it also varies with altitude. This graph is kind of fun because it came from a discussion of aviation safety and the effect of turbulence on aviation safety. And look at this. This is where most of us fly when we take long trips. And guess what? We get the most bumps. So atmospheric transmission, this kind of shows what it's like from the ultraviolet on up through to the infrared, and then into the radio. And so transmission is really quite good in the visible wavelengths where we can see things. And then as we go along into the infrared, we have these things we call windows, which are places where transmission is good, separated by areas where there's a lot of absorption and scattering. And this kind of shows where common systems for sensing the energy that comes to us are located in the spectrum. So we have the visible wavelengths, our eyes, of course, photography, which we mostly don't do except using electro-optical sensors at this point. And then electro-optical sensors can be optimized for the infrared. And then we have passive microwave, which is basically what we're doing at Simon's Observatory. And then we have imaging radar, which we use for synthetic aperture images of the surface of the Earth at this point. Let's see. So AO, adaptive optics, or AO as we call it, has basically it's basically a system whose goal is to correct the disturbance to images from objects outside the atmosphere that are caused by the turbulence in the air, the changes in density, and the distorted wavefront. Okay, quick digression. Key thing here is that we assume, because the objects are very distant, that the rays of light and the wavefront that corresponds to them is going to be flat or a plane. And so if we make that assumption, then if distortion occurs and we can remove it, then we get back to the original image. And that's what an adaptive optics system does. It has a deformable mirror, which is controlled by a computer at very high rates of speed in the several kilohertz at this point with current technology. It assumes a complementary shape to the distortion and removes it. How does it do that? Well, there needs to be an analysis of the image that relies on the fact that it should be a perfectly plain, flat wavefront, which means for a star it should be a very tiny dot equal to the diffraction limited angular resolution of the telescope. When it's not, you can find that out using a thing called a wavefront sensor or wavefront camera. This uses a technique that I won't explain here, but it's called Shack-Hartman. And then by operating in a closed loop, you get the opportunity to correct the wavefront and deliver a corrected image to your science camera. So this is a great technique for bringing ground-based telescopes into parity with space-based telescopes. The Hubble Space Telescope's angular resolution is now lower than adaptive optics equipped telescopes like the Keck telescopes. The JWST is currently has a larger aperture, so it can collect more light, but its angular resolution isn't as good as ground-based telescopes with AO either. But adaptive optics, as you can see, introduces several elements in the optical path, and it does reduce the sensitivity somewhat. So the next technology challenge is physical size of the telescopes and instruments. Bigger means all kinds of problems. I'm going to kind of slip by them here to not last too long. And then gravity, of course. You have to deal with the fact that gravity pulls on your structure. One of the things that's been done to address problems with optics, particularly primary mirrors, is, as you may know, is segmenting the mirror into a series of smaller mirrors and then having an extremely high quality way of aligning them all so that their images are properly overlapped to produce the large aperture that you want for collecting the light and having the angular resolution. Then, of course, there's noise. I'm not going to elaborate on these, but I think we know what those are. And then complexity. And this, of course, is a very common challenge in engineering in everything we do at this point. So I'm going to talk about managing the challenges really quick. This is the main discipline that I do at this point. It's called systems engineering. It's an attempt to address the problems of complexity and to provide support for the other challenges that projects face all the time, which is schedule, quality, and budget. And you can make that triangle with the thing on top that you like best. But reality is often that the cost is the thing that sits on top because you end up with a finite amount of money to do your project. So systems engineering really means a system that's multidisciplinary. Engineering is a perspective that you hold about how you want to achieve results. And systems engineering is trying to get a balance between disciplines and between all the imperatives that drive what you design and build. So one of the key things that makes us good systems engineer, which I think I am, is multidisciplinary project experience, know-how in all the key disciplines. I've designed and built things in all of the areas that are crucial here. A good set of skills at problem solving, and then the sense to choose between doing routine engineering and trying to innovate. That means choosing between cost and risk. Winning the cost and schedule conflict is usually done by adopting a certain amount of routine engineering. And on the other hand, using innovation judiciously so that you can reach the finish with your goals intact. And to do that, clear and well-defined requirements are crucial. And so developing requirements requires structure. It requires considering all the needs and wants, recognizing all the disciplines, making sure that your requirements can be traced back to their origins, that they're verifiable, and that anything that you say you have a number for, like angular resolution or signal to noise ratio, you have an error budget that drives your reasons why you think you can reach that requirement. And then the last one is no design is an island. This approach requires that you recognize that heritage can be an important part, that is solve problems or wheels that work. You can use standards because if they're done well, they represent best practices that have been vetted by an expert consensus. And then you want to follow the regulations that apply to your field because you want safety and you want your equipment to be compatible to its different parts and to other parts that you may have to introduce or interface to. So my quick thing about my different work in astronomy, the first one is the Keck Observatory. That's why I moved to Hawaii, was to take the job as the manager of the development of new instruments for the Keck Observatory. During that time, I authored or co-authored proposals to NSF and NASA that brought in $35 million in new funding over my 13-year tenure. I managed the construction of 3 new instruments: OSIRIS, a high-resolution spectrograph for the AO system; MOSFIRE, an infrared multi-object spectrograph; and KCWI, a high-performance spectrograph for the visible wavelengths. I also upgraded the high-res spectrograph, which at the time was one of the key instruments used in, fix that, I bet it's back, right? It looks okay now? I think I know what I touched.
Yeah.
There's a button on the side of my mouse, and I keep accidentally touching it. Anyway, then I upgraded that instrument. It's one of the key planet finding instruments using the Doppler technique to detect the wobble of a star because of the presence of planets orbiting it. And I also designed and upgraded the guider system at the observatory, which is what you use to acquire your field that you want to image, and then control the motion of the telescope to correct for the sidereal motion of the sky during your observation. And then I also worked on the development of advanced detectors for adaptive optics wavefront sensing. There's a picture of the two Keck telescopes. You can just pick out the segmented primary mirror, and that's, of course, on the summit of Mauna Kea. The 30-meter telescope project, I worked on that from 2016 to 2020. I was part of the AO development team. I did the preliminary design of the laser guide star system for the telescope. I didn't put anything in here about the laser guide star, but the fundamentals of it are that you project a laser beam from your telescope. Usually the center of the aperture is the best place. It is a wavelength of light that is in the yellowish region of the spectrum that's selected to excite a rarefied collection of sodium atoms that are present in the mesosphere, nearly the very top layer of the atmosphere. Those sodium atoms are there because of the disintegration of micrometeorites. And you stimulate those sodium atoms to emit light spontaneously. And that allows you to have a star in your field of view that's bright enough to run your AO system. Otherwise, if you're dependent on naturally occurring stars, the number of them that are available to you over the whole sky is quite small, and that limits your ability to do your observations. I worked on the wavefront sensing system that uses laser guide star images to drive the AO system to drive the AO corrections. And I did all these things here. One of the fun ones was the summit of Mauna Kea is approximately 14,000 feet. And for environmental reasons, we wanted to get away from using glycol-based coolants. So the choice was to use liquid CO2. And that's beginning to become the most common refrigerant, even for systems that use gas refrigerants because of their damage to the environment. But it's a whole interesting can of worms to get that to work. And then after completion of the preliminary design phase, the project had to curtail development efforts because it still, as of today, doesn't have a site. Won't go into the politics of that. They're interesting if you like to suffer and be sad. But there's the TMT on Mauna Kea. I'll just point out that its site is, I did that again. Yeah, oh, I see what happens here. Isn't that fun? All right, this time I'm back. And of course, I started over, which was a big mistake. Sorry about that. Anyway, that's a rendering of the TMT at its site. And even here, you can clearly see it's not on the summit. In fact, you have a lot of trouble actually seeing this rather giant dome from, it's 9 stories tall at the top, from anywhere on the island except this short length of coast on just north of Hilo. In any event, I then worked on the Daniel K. Inouye Solar Telescope. It's the largest, as I said, solar telescope in the world with a 4-meter primary. And I did primarily worked on the integration and test procedures and documentation. I also worked on designing a replacement for the telescope's heat stop. One of the things that's interesting about the telescope is with that 4-meter aperture, it collects about 12 kilowatts of solar radiation. And we need to get rid of all of it, but about 300 watts before we send it to the AO system. So that was a success. And this is a picture of the observatory. It's on Haleakala on Maui. And there's a picture of the telescope. The primary mirror is down here. It's a Gregorian telescope. The secondary is up here, and the heat stop. All of the optics in this telescope are either liquid or air cooled. So it's quite a challenge to deal with the heat from the sun. And one of the things that's really cool is we got our first light AO image of the surface of the sun on the cover of the New York Times, and on the first page, I should say, of the New York Times. These little things that look like caramel corn kernels, each of them is roughly the same size as the state of Texas. And this is what you would see if you were 4,000 kilometers from the surface of the sun, right about when you melted. But the adaptive optics system is able to correct for the turbulence in the photosphere of the sun and the turbulence in its coronosphere, and also the effect of the heat from the sun as it reaches our telescope. And it produces very high resolution images of the surface of the sun. Now I am the lead systems engineer for the Simons Observatory. I'm responsible for all of the requirements, interface control documents and test plans, and I'm the ultimate authority for technical decisions in the implementation. I have performed some design activities, especially for mechanical and electrical electronic systems, to make sure they'll last in the hostile environment of the Atacama Desert at 17,000 feet in Chile, of course. Here's two pictures. This is a picture of the site of the observatory. These are 3 ground shields, the big round circle there. And in the center is one of each of the 3 small aperture telescopes. This is the small aperture telescope. It's just under a ½ meter in aperture, and it's a refractive telescope, has 3 lenses made of silicon. And then what's really fun about these is that the detector focal plane are cryogenic detectors that use superconducting junctions to make the highly sensitive measurements of that 2.2 and change Kelvin radiation. The focal plane operates at temperatures of less than 100 millikelvin, so less than 1/10 of a degree from absolute zero. And the detectors are then read out using a technology that's similar to what's used for detectors in MRI, magnetic resonance technique, and then the data is transmitted to a computing system on the site in this high bay building, well, this office extension of the high bay building, and then remotely to the observers around the world, actually, because this is an international collaboration. This over here is the still under construction large aperture telescope. It has a different job. I'll tell you more about what the job of these is in just a second. Its job is to look at gravitational lensing and to try to make measurements of the cosmic microwave background at high resolution using gravitational lensing by galaxies distant from us. Let's see. So the small aperture telescope's main job is to try to detect the effect of gravity waves on the cosmic microwave background. And those gravity waves are from the Big Bang, if they're there. So the cosmic microwave background has energy emitted at all different polarizations. Those polarizations are present because of the perturbations caused by the gravity waves. We use a system to separate out the angles of polarization. In fact, our detector array has sensitivity to 2 different orthogonal orientations of polarization at each of its wavelengths. And then to detect those, the presence of those particular polarizations that we think are predictive of the existence of the gravity waves that we believe are there from the Big Bang. So I think I'm done.
Wow. Thank you very much, Sean. Boy, did you ever cover an awful lot there.
Yeah.
Most interesting. Good thing I wrote down a couple of questions here. Since I'm talking, I'll take a stab at one question. Anyways, here you meant back that our solar system is full, so I'm assuming you meant if a planet, we didn't have to worry about planet-sized objects. So does that mean to say that if a planet-sized object was heading this way, it would bounce off our solar system?
Well, what it would, I mean, it might not be totally free of consequences. It could, in the worst case scenario, get in proximity to something inside the orbit of the former planet Pluto that would damage or disturb a nearby object. The way the gravitational presence, if you like, of Jupiter and Saturn in particular work, they would not allow an object from outside the solar system of sufficient size to interact with their gravitation in a kind of give and take way to enter the inner orbits. So we're Jupiter and Saturn are our shields, if you like, to protect us from rogue objects of any size. Of course, the moon helped protect the Earth from a lot of asteroids, but we're not out of the woods on that. There's still threats, and we're still not doing a good enough job of mapping all their orbits. That's a whole other subject. But in essence, there just isn't any way for an object from outside the solar system to enter into the orbits of the inner planets, and there's no way for an object from outside the solar system to take up residence in orbit around the sun, at least not in terms of where the orbits of the existing planets are. Does that make sense?
Yes, interesting. Okay, got a bunch of other questions here. So Dave is up next.
Yeah, fantastic presentation, Sean. As always, anytime you talk about this stuff, you have several of us just glued hanging on every one of your words. I could sit here and monopolize you all night, but I'm going to limit my questions. I've got a bunch, but I'm only going to ask a couple, and then I'll go back at the end of the queue, and this way I'll allow everyone else to ask questions. So the couple things. One, I've always been fascinated in spectroscopy in astronomy. How you take a star and you're able to look at that and say, okay, it's got a hydrogen line, it's got a sodium line, it's got this, that. Because if you look at the image you're getting from that distant star, it's very small. Now, optically, you can't get enough light coming in. You would have to maybe integrate it over time or do something. But how do you, and it's kind of interesting because you said you did work on the spectrograph project. I think it's the same thing
Right.
asking about, but how do you actually get sufficient light to be able to do a spectral analysis?
Well, the key thing is that you're able to observe for a long time. Most of modern astronomical observations with large telescopes last anywhere from 10 minutes to several hours. And that's where that guider system upgrade I did for the Keck telescopes comes in. The accuracy with which the telescope can move in azimuth and elevation to track your object that you're interested in is very important, because if you're talking about a spectrograph, for instance, if it's an instrument like HiRes, which is a slit spectrograph, you have to keep the object on the slit. You don't want it wandering around because you lose light. Then you have detectors that even in the visible wavelength range, which is where HiRes operates, the detectors are cooled. They're cooled down to the temperature of liquid nitrogen, not to the insanely low cryogenic temperatures that the bolometer arrays use for Simon's Observatory. But nonetheless, it's fairly cold. And that's purposefully done to get rid of as much of the thermal noise as possible, and to make the detectors as quiet and sensitive as possible. Detector technology has been a key thing in doing that. But the simple answer is you just simply integrate it for as long as you can. And that could also get stopped by a change in the weather. But that's the simple answer. Yeah.
That's what I kind of figured. It was an integral over time. You're integrating the signal over time, but the resolution, you've got this tiny, because you mentioned about a slit. Say you have to get the object within the slit. You have to have your detector be able to look at a tiny spot.
Well, of course, what you do there is you have an optical system that first of all takes the light from the telescope and collimates it so that all the rays are essentially parallel, and then they the light goes to a device that splits it into the different wavelengths that you're interested, into a spectrum. Usually that's a diffraction grating. And then you take the light that comes off the diffraction grating, which is still, if the grating is good enough, a series of parallel rays, and you focus them using a camera, basically, onto the detector. The detector is quite a bit smaller than the entrance aperture of your spectrograph, and that's way smaller than the entrance aperture of the telescope. But the light from the 10-meter aperture is, of course, concentrated, as you're saying, into a tiny spot. We're typically talking because again, we're talking here about a scene limited instrument. So we're talking about something like 1 to 3 arc seconds in what we consider the acceptable range of seeing, and that image is a function of what the plate scale, as we call it, is, which is the physical size that is produced by the magnification of the telescope. So the image is not that small when it gets to the focal plane of the telescope. And I'm going to be able to quote off the top of my head what size that is. But when the image reaches the detector in the spectrograph, we use in high res, the detectors are 2,000 pixels by 4,000 pixels. Of course, those are really the power of two numbers, not exactly those, but it doesn't matter. And each pixel is about 13 microns in diameter. And we cover the entire image array with the spectrum. So it's not tiny by the time we reach the detector. And it's not tiny at the focal plane either. When the telescopes were first built, and there were no instruments yet, but they were celebrating the existence of the telescope and the functioning of the first portion of the primary mirror, they actually took a rear projection screen and put it in front of one of the Cassegrain, not Cassegrain, one of the Naismith foci. They're a focal station that looks through the elevation axis of the telescope, because these are altitude azimuth telescopes, like so-called gun turrets, if you like. And they put a rear projection screen there, pointed the telescope at the moon. The moon covered nearly the entire Naismith platform opening, and it was really neat looking. So.
Yeah, so I got one other quick question, because as I said, I could monopolize you all night. Yeah, that's actually, we could go down that rabbit hole about how that's done, but it's very, very, very interesting. The other thing, you mentioned gravity, and it made me think that, okay, I understand gravity is a problem with mechanical things. You got big things and you got lots of forces and stuff, but what about the optics? Because like glass and mirrors, it's a very viscous solution, and the resolutions and the sensitivity you've got. Do you get any problems with distortion because of the gravity on the
Right.
glass itself? And is there a lifespan or a correction you have to apply?
Well, there's a couple of things that are of interest there. One of them is that as you build bigger telescopes, you need bigger mirrors for them, because first of all, a refractive telescope bigger than about 100 inches is just impossible to build. That was learned a long time ago. Modern times, with all the better fabrication techniques we have, you might push that a little bit. But for the reasons you state, that's a key issue, because, of course, any well-corrected optical system where color aberrations and other chromatic aberrations and other issues are addressed is going to have more than just 1 or 2 lenses. And maintaining the alignment of those lenses when they're separated by the fairly large distances you need to get the magnifications you want with reasonable curvatures and thicknesses, all those optical trade-offs, is really almost impossible to do. Now, you could conceive of a servo system that would compensate, but this is one of these things where if you say, I'm going to do it a certain way, you've got to unravel what you have to do to get to the performance you want. And you probably would find in that case, that you have to have actuators and sensors of such incredible precision that you can't afford to build them if you can even make it. You can't afford to build the telescope, even if you can make that system work. So we went to reflective optics. And the Keck telescopes are the first ones to solve the problem you're talking about, which is The largest telescopes with a single monolithic mirror are 8 meters in diameter. Those are the 4 telescopes of the Very Large Telescope Observatory in Chile, operated by the European Southern Observatory, and the 2 telescopes of the Gemini Observatory, one on Mauna Kea, one in Chile, and the Subaru telescope. Those are 8-meter mirrors, single monolithic, as we say, figured to the desired performance and quality, but they have a mechanical support structure behind them of actuators that adjust the figure of the mirror because it sags when you tip it away from the zenith. So even at 8 meters, there are problems. Well, to go beyond that, the solution that was developed for the Keck Observatory, and is also how the primary mirror of the 5.7 meter aperture of JWST and the Telescopio Gran Canaria, which is a 10.4 meter telescope, like that matters, but it is, and all of the extremely large telescopes that we're either want to build or are trying to build, the TMT on the want to build, and constructing the European Southern Observatory. There's another extremely large telescope called the Giant Magellan Telescope, which is not the same approach, but I'll mention it in a moment. Each of the mirrors in the Keck telescope are 1.8 meters across, and they're a hexagon shape, and they're all nested together to make a great big irregularly shaped scalloped edge, if you like, mirror that's actually a little bigger in its actual effective aperture than 10 meters, but we call it a 10-meter telescope. Each of those mirrors has its own set of actuators that allow it to be adjusted in position relative to all the others to keep the mirrors acting as one giant monolithic mirror. And that compensation is adjusted as needed as you go from zenith to horizon. And that's how the problem was solved.
That's fascinating. Absolutely fascinating, Sean. But let me stop and let me turn the baton over to someone else.
Okay, Michael, you're up next.
I had a question. I missed the beginning of the presentation. I'm not quite sure whether this is particularly relevant, but I was wondering about the Starlink constellations. I think there's something like 7,000 satellites up there now. And what impact is that having on astronomy for you?
It's non-trivial, especially in the visible wavelength range. The constellations, as they orbit the Earth, they reflect light from the sun. It depends on where they are in their orbit, what the season is, and so on, where the Earth is in its orbit around the sun, in other words. And they are a significant problem. It's something that's being discussed at length. It's not clear how or if it can be resolved. But right now, the desire is to prevent it from getting worse. That's the short answer.
And my understanding is that Elon Musk and company are talking about putting many more thousands of these up. It's going to make it much, much worse, isn't it? You would think.
Yeah, although interestingly, there is a discussion happening at various levels between SpaceX and the National Science Foundation about how to address this problem without, denying the ability to have this communication system. Another fun fact is that's not the only kind of constellation of mesh network satellites that's being launched. The Chinese are in the process of starting to crank out their own version of that. And if you think they're going to give a you-know-what about its impact on anybody, you probably need to rethink. It's not going to be fun. So.
Okay, thank you. That was very interesting and a very interesting presentation. Thank you.
Well, thank you. Thank you.
Joe, do you still have a question? Your hand was up.
I had the same question as Michael did regarding the impact of the satellite constellations, but I'll just say, fantastic presentation. I'm loving it.
Oh, thank you.
Okay, Drew, you got a question?
I do. And an observation, I wish you did a podcast.
I have friends that do them, and I've learned that they're hard to do, really, to sustain anyway.
You sure got I can understand, but sure, from a greedy audience point of view, I could listen to this, like Dave said, for a long time.
Yeah.
I've been reading a little bit about people doing amateur radio astronomy using SDRs, and I was wondering if you'd encountered people who have tried this, whether they actually put some cooling on the SDR to kind of reduce noise, size of the dish they might use. Typically, I think the biggest one we can get our hands on is something around 4 feet or about a meter. Will you even see anything if you do a scan across part of the sky with an SDR?
Well, it depends on what you want to observe. I mean, there's lots of radio astronomy sources, um, and it's some of them are interesting. Uh, it's largely, I think, going to be an exercise in detecting things that we've already observed in larger and more I don't want to say better. Well, they are better facilities. There's engineering that's been done to make them better. As far as cooling things is concerned, by the time you're into the SDR, you're in the digital domain, and you're not really going to be benefiting except to keep the thing from overheating by cooling it. The place where cooling could help is that when you make the transition from the field of electromagnetic radiation into the antenna, you immediately start sacrificing signal amplitude. So it's common, of course, to put what they call a low noise amplifier, or LNA, as close to the antenna as possible. They definitely work better if they're cooled, but we're probably talking about cooling them below the temperatures you can do with Peltier cooler.
Right.
Although a 2-stage or 3-stage one might get you something. That's the place where cooling would matter. As far as aperture size is concerned, of course, you can always think about designs for receiving arrays or individual receiver antennas that don't have to be parabolic dishes and that don't have to be expensive. There's techniques you could get into that would help you there. The other thing that, of course, amateur radio astronomers do is they track satellites. And that's, of course, interesting because a lot of the satellites that our government doesn't want us to know about are up there for defense purposes. And although you can't decode their transmissions, you can still watch them go by.
Thank you.
Eric, you're up next.
Okay, sorry, just had to unmute there. Question for you, Sean. Very curious about the adaptive optics topic that you're discussing. I'm just curious, how long has that been? What's the sort of history of that in a nutshell? And also, as a follow-up, do you see that as? I mean, obviously, it's a very high-end process. Do you see that scaling down anytime to smaller scale applications? So it's not going to be just the scientific equipment, but is that something that you see in a reasonable time frame coming down to a to a more almost, I won't say amateur scale, but something a little bit more manageable cost-wise? I assume it's a very expensive process at the moment.
Okay. Well, the first part of your question, when did we start doing adaptive optics? That actually was developed in the late 1980s by the Air Force Research Laboratory in Albuquerque, New Mexico. Of course, something that doesn't get a lot of attention but is interesting nonetheless is that since we and our competitors, if you like, in the world, or our opponents, depending on your view, have been launching satellites, we've been trying to look at those satellites from the ground using telescopes. And the Air Force operates a couple of facilities for space surveillance. And the research and development of those facilities is done at AFRL in Albuquerque. So an adaptive optics system, first using light from stars, and then later light from the object itself, and then ultimately from guide star lasers, started in the late 1980s. It was classified for several years, and then in about 1992 or 3, the Air Force decided to declassify it and make what they had accomplished so far available, because they realized that it would be very beneficial to astronomy and would, of course, then allow them to take advantage of all the developments that would occur in astronomy to improve their capabilities. I actually worked on detectors for the Maui Space Surveillance Facility, which is their production facility, if you like. It operates every night. The one in Albuquerque is really a research facility. Probably the most well-known example of the use of this capability was when the space shuttle Columbia was in trouble with the loss of a tile. They did make an attempt to image it and try to get an idea of where the tile was that was missing. They probably knew from those images where it was, but as we know, NASA made a bad choice and decided to let them come down anyway. As far as the use of it by amateur astronomers or with smaller telescopes, the most productive thing to do with, say, less than a 1 meter aperture is to have an image stabilizer. And that's commonly done by actuating the secondary mirror in the telescope with a high-speed actuator, and you have a sensor. You have to sample a little bit of the light, so that does, take a little of your light away from your science exposure, better from your eye. But it operates the same as a more sophisticated AO system. It tries to concentrate all the light in one place using a closed loop system. And those are actually quite good. They really do improve your image quality. There are very small deformable mirrors now that aren't that expensive. And I think some amateurs have taken their 1 meter class telescopes and added an AO system to them. One of the problems is that I didn't go into this, but because the atmosphere aberrates the light from shorter wavelengths more than it does longer wavelengths, to really take advantage of adaptive optics at any aperture using available technology, you're pretty much still working in the infrared. And building a telescope with good infrared sensitivity is really hard. That's why most amateurs don't try it. Does that help?
Yes, that's great. Thanks for the detailed answer. Appreciate it. Yep, perfect. Thank you. Thanks, Sean.
Okay, Hassan, you're up next.
Okay, I missed the great presentation, near and dear to my heart. So I have to ask, before I ask my question, I have to ask, are you primarily talking about like SDR, like radio astronomy, or optical astronomy?
I was talking about basically the whole range from the visible wavelengths through the near, mid, and long wave infrared, and then also into the radio spectrum. But in this case, the radio spectrum portion I'm talking about is from about 60 gigahertz to 280 gigahertz. It's technically microwave astronomy, but it uses imaging techniques. Just the lenses are made of silicon instead of other optical glasses. Excuse me, and they are the detectors are cooled cryogenically to extremely low temperatures.
Okay, so I have a question that covers both. How soon before we have an observatory on the far side of the moon, and would it be a perfect observatory?
Well, the first part of that question entirely has to do with politics and funding. My guess is it's going to be a long time because it's probably not going to be a priority. The second part is I don't think it would be a perfect observatory. You're correct in saying that it would be free of some of the limitations that space-based telescopes have, which I did mention as I was talking about it briefly. But on the other hand, you would have to assemble it on the surface of the moon. At some point, you'd have to contend with the temperature. You'd have to contend with the dust which, you know, any activity you engage in would potentially disturb the dust, and the dust is not going to fall right back to the surface that quickly. And of course, then you'd have to decide if it could be totally robotic or if it was going to need people. And doubtless those people would be making, you know, trips in spacecraft or vehicles from the near side to the far side. Yeah, it's got a lot of issues, but
Okay.
of course it could be a good thing.
Yeah. So on that note, if you have to make antenna elements, they basically, you know, on Earth we do them out of metal because you want to move electrons through them. In a vacuum, you don't need the metal. You can just move the electrons through free space. So can you just have electron beams, you know, going over hundreds of thousands of kilometers and essentially acting as antenna elements?
I'm not sure I quite understand the physics there. If you have a coherent or at least a confined beam of energy, you would have to work pretty hard to derive from that a signal, which I guess would be because external electromagnetic fields are impinging on it. I mean,
Yes.
I haven't really thought about how you do that, but I guess I don't think it's better than using antennas of a more conventional type. But yeah, I don't know. I'm not an expert on the physics of something like that. That's for sure.
Okay, because I've thought about this for a while, and in theory, you could make a giant antenna on the far side of the moon made of nothing at all, just empty space and a bunch of nodes, electron beams and emitters, and they'll travel in straight lines, and then receivers. So you could really do like super low frequency astronomy easily.
I guess you'd have to think about what you'd be detecting, what is on offer there in the way of electromagnetic emissions from, you know, from space that
Yep.
you'd want to detect in a method like that. So I guess I don't have a lot else to say about it.
Okay, all right, thank you.
Well, Hassan, you can let us know when you finish building nothing out of something, and then let us know how that went.
Yep.
Dave, you're up next.
Yeah, it's an interesting concept what Hassan said, but yeah, Sean, you're right. It's you've got all kinds of EM, you know, impinging on that, all kinds of stuff which could perturb it. Whereas if it's in a metal, I don't think you would have a big of effect because you've got the electrons bounded to something, right? And you don't have enough energy to rip them free. I don't know. Again, but anyway, let me get to my questions. First one, I saw this. It's science fiction, and I just want to know if there's any reality to this, because I just saw a program the other day. It's a science fiction program, and they were talking about the microwave background radiation. And in the program, they were talking about a spot where there's a null. Now, it seemed to me that, you know, because it's background radiation, it would be right across all bands. But is there such a thing as there is a null, or there's peaks and valleys in the microwave background radiation?
Well, for all practical purposes, the temperature of that background is fixed at that 2.2 and change, 2.275, I believe it is, degrees Kelvin. It's fixed at that temperature, which in turn determines what you need to do to detect the microwave emissions from it. Let's see if I'm going to get this make sense here. The idea of some kind of, well, first of all, it occupies a range of frequencies that are in the microwave spectrum, and so you can decide which frequency band you would like to try to observe it in. There are telluric effects, as we call them, effects from the Earth's atmosphere, and also effects from interstellar dust that give you windows in the microwave spectrum, just like they do in the infrared. So you have to avoid those because those are noise signals that you don't want in your data. The way in which you might have a null, but I don't believe there is an actual one, would be in the intensity domain, where the distribution of energy isn't uniform, and we know that. But is there a spot where there's none of it? I think the answer to that is no, and you answered that question already. It's just a lot weaker, and that's because of the anisotropy of its original distribution.
Yeah, because that's what I would think. It's like a noise floor, right? It's there, and for you to see it, as you said, you have to make sure that other noise emitters, you compensate for that in order for you to see that complete floor. Now, the other thing I wanted to ask, and that was purely science fiction. I kind of didn't believe that, but I just thought,
was their idea that something was hiding in there? Is that it?
No, they were. They called it the cosmic watering hole, and they were saying that's the frequency at which, if you're going to contact an alien civilization, that's the frequency you would use.
Oh, okay.
Because,
yeah, I think
because it had less of the cosmic background radiation at that one frequency.
Oh, I see. Okay. Well, I don't think such a thing is actually true, but I guess one couldn't say for sure.
We'll show up 4 days of May next year.
And the more commonly held view about how to do this actually is to choose recognizable emission lines from stars and their atomic constituents, which is basically the hydrogen line. That's the one that shows up in the radio frequency spectrum, and that's the place where most people think if you wanted to build a powerful transmitter, you would build it so it was narrowly placed around that line because everybody knows where it is. I think that's the
good point. It's like a fundamental in the universe, right? Yeah, that's good. I do have another question, but the time here, let me be cognizant of time. I'll save it for when we're down at the Holiday Inn bar.
Next year in May. Yay. Yeah, looking forward to it already.
Okay, does anybody else have any questions?
Thank you very much, Sean. That was great. Thanks.
You're welcome.
Joe, you have a question.
Sorry, yes, I do. Sean, I was doing some thinking about, as you were talking about various telescopes. So, for example, telescopes on the ground, versus what we're seeing with James Webb, and also with what we had with Hubble. I was curious, in any of the time that you were involved with your various projects, do you know if there was any discussion at NASA of actually putting a large optical telescope on the International Space Station, like something on the scale of something like Hubble? Because when you put something up in space, obviously it's difficult to be able to do repairs and whatnot. But I was just realizing or thinking that if you were to put the telescope onto the space station and you've got astronauts there all the time, and that you're sending up payloads, that the possibility of doing changes or swap outs of stuff could happen. Do you know if that kind of discussion ever happened?
Well, I don't think so. And I think the reasons probably are that this International Space Station is already pretty big. So this would be an addition to its mass that might not be considered a good idea. The other thing is that the International Space Station has a pretty big heat signature. So it would be kind of hard to do infrared observing and control the background. Of course, it's in a low Earth orbit, so it's constantly orbiting the Earth, but so is the Hubble Space Telescope, so that isn't really a problem. It's not in a geosynchronous or fixed location with respect to the Earth. Let's see what else. it's true that it could be maintained more easily. I think it would be hard to even put a telescope the size of Hubble into the collection of modules that represent the International Space Station. But I also suspect that because we've been lucky and Hubble's lasted so long, there's little or no motivation to study it. So short answer is I can see reasons not to do it. I don't recall ever hearing it discussed, but it probably has been.
Thank you.
Okay, I have a quick question here. I think we were talking about adaptive optics earlier, and to cure distortions in the atmosphere. What about the distortions and stuff that you get in space itself? You mentioned earlier, like for example, cosmic dust, and who knows what else is out there. How do you adapt?
Well, yeah, the thing that in interstellar space or intergalactic space, the only thing that really causes aberrations that you could detect and correct with AO are gravitational fields. And that's where, the subject of gravitational lensing comes in. Light that passes very close to a massive object, from our point of view, is distorted and bent around the object. And we've actually developed techniques, which is one of the things we plan to use with the Large Aperture Telescope in the Simons Observatory. We've developed techniques for understanding how those little slivers, if you like, of light that surround the massive object can be reconstructed into an image. And so we can use a galaxy as a telescope to get an image of something that we otherwise couldn't see well, which is pretty neat. The image quality isn't the greatest in the world, but you can learn a lot still about what you're looking at from those techniques. Things like dust and in fact gas. A good example of this is the center of our galaxy is a region where there is quite a lot of between us and the center of our galaxy. In fact, there are lots of clouds of dust and gas. They absorb most of the visible light that comes to us from the center of our galaxy. And to see the center of our galaxy, the stars that are orbiting the black hole, we have to use infrared, and that gets us through that obscuration. But in terms of what we're talking about timescale wise, those obscurations are pretty stable. They don't change over time in terms of our exposures that we want to make. But the atmosphere does, and so correcting for the atmosphere is what we really need to do. Does that make sense?
Yeah, it does. Yeah. Got one more question I think we got here. I don't know what your time is like there, Sean. We don't want to.
Oh, I can go for another 10 minutes anyway, I think.
All right. Hassan, you got another question?
Yeah, I just saw in the news today that Chinese claim that they can actually use Starlink satellites to detect stealth aircraft. I'm just wondering if I'm just curious if you know how that's like. Are they just doing occultations or diffraction off the plane? Because obviously, if it's absorbing radiation.
My first impulse is to say they're doing some kind of passive radar. Because we have a technique that's fielded in our defense community that uses a passive radar system, where what we use terrestrial broadcasting stations as the signal source, and then we detect them with a giant patch antenna. And so I wouldn't be surprised if that isn't what they're doing.
I'm curious.
In fact, be using the emissions from the satellites themselves as the passive radar signal source. I see Kevin smiling. He must know something about this field.
Kevin? Well, I guess a follow-up question is, can you use the galactic hydrogen, the 1514 megahertz signal? Because it's kind of a band across the sky. So could you use that to do the same thing?
The signal, the problem is it's a very weak signal to start with. Otherwise, we wouldn't be able to do anything. So it's not a powerful source of EM that you would be able to detect reflections from very tiny things. I mean, the angular size of a Starlink satellite is pretty darn small. And I think the fact that they're in constellations is the only reason that it even has a chance of working. but I have to say, if they've announced they can do it, I'm sure we've already figured out how to do it. So I haven't heard
Yeah,
about it though.
yeah. If using passive radar, you would want a strong signal. But if you're just looking for occultation, like a dark object moving against a bright background, then it's a different story. I guess you'd have to track it
Yeah,
with
the
a telescope.
problem is you have to be on the line of sight to the source. In this case, the reflection from the Starlink satellite of the sun. Then those satellites have to pass over you, and the thing you're trying to detect has to be between you and them. And I'll have to tell you, if the stealth aircraft is already there above you where it can occult those satellite images, it's already there to do whatever it's there to do. It's kind of over.
Yeah, you'd have to build it like 1,000 kilometers out or something, so you get about I don't know 10 minutes or whatever. So yeah, because if it's occultation based, you just have to point it upwards and have enough angular resolution to cover a line along the plane of the Milky Way, and you just look for a blip in the signal.
Yeah, I think you have to work out what the angular sizes are and how big of a dip you'd get, and whether you could even detect it reliably first, though.
Right. Okay. Thanks.
Kevin has a question.
Yeah.
Well, no, I just did a Google search on that thing that Hassan was talking about. And the paper that they were talking about that did this, they used a DJI Phantom 4 drone to test this. It's not actually, well, they don't admit that they've tested it with aircraft. So it's kind of a proof of concept thing by the looks of it.
Okay. And is it an optical occultation of the constellation? Is that what they're doing?
Well, they're not, they say it detects the distortion in the waves come, like the radiation from the satellites. So it may be occultation, but maybe there's some reflection or refraction happening too. Diffraction. Sorry. Yes.
Well, okay. So are they actually? I mean, okay. So that leads me to conclude that they might be simply looking for the effect of this object on the signal that's coming down from the satellite, right?
That's what it seems like.
Yeah.
But,
so the satellite's providing an RF source that's then being affected by the presence of the object. Yeah, I guess so. Again, it's still line of sight, though.
Yeah.
That's the limitation, I think, might be the killer.
Yeah, it's the Earth is a big place, and even with thousands of satellites, it's still a really big place. So anyway.
Cool. Sean, I have a quick question here. Earlier on, you're talking about the temperature of the cosmic background radiation at something like 2.7 Kelvin, I think it was. Is that the coldest we've ever measured?
No. I mean, we've in laboratory settings, we've actually taken things down to what's essentially absolute zero, where all molecular motion stops. That's been done in laboratories. We've done things like make so-called metallic hydrogen, which is hydrogen that's so cold that it's the space between the atoms is small enough that it becomes electrically conductive and qualifies as a metal. No, it's really a statement about how hard it is. Yeah, 2.725. I think I said 275 earlier, which was wrong. It's just an indication of how difficult it is to do the detection, because obviously most everything else in the universe is warmer than that.
Yeah. Including where I was 2 weeks ago camping. Anyway.
Did you say metallic hydrogen?
Yeah.
You used it in the detector?
And
what I thought there was like minuscule quantities. Oh, sorry.
Well, that's what
I thought that we had minuscule quantities.
Yeah,
I thought there was like minuscule quantities of it.
Okay. Yeah.
So do they have metallic hydrogen quantity enough?
No,
because I thought it was like minuscule quantities of that.
Yeah. I don't know what I said that led you to believe I thought there was a lot of it. It's just a phenomenological thing that they did to prove that they could do it. I think really, it just happens to be that it's a metal. It becomes a metal. It becomes a conductor of electricity. It's one of the criteria for being a metal, I think.
Is it a superconductor though, or at room temperatures? Or?
No. Metallic hydrogen only exists if you take some hydrogen, you liquefy it, and then you keep cooling it until it turns into a little ice cube. And you're right, it's tiny. I don't know what the sizes are, but they're very small. And it only stays that way as long as you keep taking away heat from the apparatus in which you've chosen to contain it.
Yeah, because I've heard that metallic hydrogen might be stable at room temperatures.
No.
Oh, okay.
No.
Okay,
Thank you.
we're getting pretty close to the end here, I guess. Is there any last minute questions? Anybody have any quick questions, comments? Okay, well, Sean, well, thank you so much. Been looking forward to this one for quite some time, and most interesting. And I thank you for taking the time to talk to our group.
Yeah, well, I enjoyed the opportunity greatly, and maybe I should just drop in for one of your other programs just to see you guys again.
Well, you're most welcome. Pretty much the 2 Wednesdays, the 1st and the 3rd, we're around here at the same time.
Cool.
Okay, well, thanks again, Sean. Appreciate it very much, and we'll catch up with you soon.
Thank you to you guys. It's great to get to know y'all. Thank you.
Okay, great.
Thanks, Sean.
All right,
Good
thank
presentation.
Thank you. Fascinating.
Yeah.
Bye.
Okay.
Cheers, everybody. Thanks for joining tonight.
Yeah. Bye-bye.
Yep. Good night, everyone. Take care, Sean.
Night all.